here is our second video of our lesson for this week, the Pythagorean Theorem for right triangles. And so this is a really important concept. The Pythagorean Theorem formed many years ago. So let's talk about it. So the Pythagorean Theorem. Pythagoras was a guy that lived 500 years before the current era, or before Christ, in ancient Greece. And so he was into, and this is an activity we do in class, you might recognize my handwriting there, but he had this right triangle, and he said, I noticed something about the areas. If I put a square over here, and he drew it, and then he drew a square over here, the length of this leg here is 6, and the length of this leg is 8, and the length of this side is 10. And so he drew squares, and of course, if it's a square with sides of 6 and 6, that's an area of 36. And here this square is 8 times 8, and that's 64. And then he said, well, this is 10, and so this is 10 times 10, and that's 100. And he said, oh my gosh, look at this. If you add these legs, here's the right angle right here. If you add these legs, which are on opposite sides of the right angle, the square of those, or the areas, you add those together, it equals the area of this diagonal length here. And we call this diagonal length, the length across from the 90-degree angle, we call that the hypotenuse. So he said, well, 64 plus 36 equals 100. And so I know I can look at these areas of these squares, and maybe I could work backwards and find the length of these sides. And if you're a fan of movies, the Scarecrow, and in The Wizard of Oz actually says this, but he says it incorrectly, but the sum of the square of the legs of a right triangle, here are the legs, and if we add the squares together of the right triangle is equal to the square of the hypotenuse. And the Scarecrow said that in The Wizard of Oz. And so here is the Pythagorean theorem. Leg squared plus leg squared equals h squared. Sometimes they call these legs a and b and the hypotenuse c, but I like saying leg squared plus leg squared equals hypotenuse squared. A squared plus b squared equals c squared. You see that down here. A squared plus b squared equals c squared. Okay, next slide. So, can we use the Pythagorean theorem to find the length, the missing length of a missing side, or the missing length of a right triangle? And the answer is yes. So, the first thing we have to do, if we're given 2 of the 3 sides, is we have to identify which is the hypotenuse. So we'll say here, in this case, the legs we have are 3 and 4 feet, and the hypotenuse across from the right angle is right here. We're missing it. And so the next thing we would do is write the Pythagorean theorem, substitute in the values we know, isolate the squared value, and take the square root. I'm going to show you this example on the next slide. So here we have the missing side, and I write down the sides that I know. The leg is 3, and the leg is 4, and the hypotenuse I don't know. I wrote down the Pythagorean theorem. That's very important. We're going to substitute in the lengths, square them, and in this case, since they're on the same side, we might as well add them together. And now I see, well, the hypotenuse squared, using this here, is 25. But I don't want to know what the hypotenuse squared is. I want to know what the length of the side is. So to do that, we have to do the square root of both sides. And the square root of 25 is 5. And the square root of h squared is h. And so we found this length here, 5 feet. 3, 4, 5. If you have any construction workers in your family, they know about a 3, 4, 5 triangle. That's how you test to see if a corner is square. 3, 4, 5 triangle. You'd put a nail here and measure 3 feet and 4 feet and adjust this to be exactly 5 feet. So, and that we have another vocabulary word. It says, since all 3 sides are perfect squares, 3, 4, and 5, this is called a Pythagorean triple. And there are lots of Pythagorean triples. I thought I'd share with you some of them, 3, 4, and 5. 9 plus 16 equals 25. There you go. How about 6, 8, and 10? We saw that in our first example. 9, 12, and 15. So 81 plus 144 is 225. And so these would be right triangles. But these are fairly rare, and so we have a lot of sides that have square root lengths. And as we remember, those are irrational numbers. So what is the missing length of this right triangle? So let's do a couple more examples. So here, first thing is we identify the hypotenuse, and we're given the hypotenuse in this case, so that's 8, and I write that down. And we have 2 legs, and one of them is 4, and we have to find the missing one. Well, we always write down the Pythagorean theorem, and now that we know a leg and a hypotenuse, we're going to substitute those in there. We're going to square the leg, that's 16, and square the hypotenuse. And now if you see, we have an equation forming here. So I have L squared equals 48. Again, I don't want to know what the area of that square is. I want to know what the length of this side is, this leg. And so I'm going to take the square root of both sides. And the square root of 48 is the answer. That's the length. However, that's not a perfect square. So it can be simplified, the square root of 48, since it's 16 times 3. Well, the square root of 16 is 4. And the square root of 3, of course, is an irrational number. So we could write it like that. But if you want an estimate of what the square root of 48 is, we know that the square root of 49 is 7. So we know that the square root of 48 is very, very close to 6.9. And of course, it's an irrational number, but it's 6.9 is a very good approximation for the length of the square root of 48, or 4 times the square root of 3. Let's look at another example. What if we are given one of the sides in the form of a square root? We see that often. And so, not often, but sometimes. And so, first, let's identify the hypotenuse. The hypotenuse is the square root of 50. So that's a little bit over 7, isn't it? But we're going to use the number exactly. So I write down the Pythagorean theorem, and I have one of the legs and the hypotenuse, and I substituted those in there. And 6 squared is 36, and this is where I'm going to slow down a little bit. The square root of 50 squared is 50. So if you square a number and take the square root of it, these cancel each other out, and you just left with the number 50. So here, the square root of 50 squared, because that's the hypotenuse squared, is just 50. So remember that whenever you square a square root, it becomes the number inside. And so here by solving, I get L squared equals 24. And I take the square root of both sides. Again, always the last step is taking the square root of both sides. And we see that the length of this side over here is the square root of 24. Of course, that's 4 times 6. So the square root of 4 is 2, and the 6 stays inside. And there is a lesson on how to simplify square roots, and you'll just have to, hopefully you kind of get it. Now, an approximation for the square root of 24, since the square root of 25 is 5, we could say that the square root of 24 is very close to 4.9. And so this length is very close to 4.9 meters with a square root for one of the sides. All right, and so the next concept uses the idea of, well, we're not finding the sides of a triangle, but what if I give you the 3 sides of a triangle? Can you tell me, is it a right triangle? And so the converse of the Pythagorean theorem, it's determining if 3 sides of a triangle form a right triangle. If the lengths of the sides of a triangle do not satisfy the Pythagorean theorem, the triangle is not a right triangle. If they do, they are. And so, let's see here. Do 6, 8, and 10 form a right triangle? And so, this is just a matter of checking to see if both sides are equal. So I wrote down the Pythagorean theorem. I substitute in the numbers, and I added these 36 and 64 together, and I get 100 equals 100. So the answer is yes, 6, 8, and 10, those lengths do form a right triangle. How about the next concept? Do the sides 3, 5, and 7 form a right triangle? Again, let's write down the Pythagorean theorem, and we put the numbers in there, 3, 5, and 7, square them, and then we add 9 and 25, and we get 34 equals 49. Well, it's not equal, so we know this is not a right triangle. In fact, we can think of this hypotenuse side, which is the diagonal, if we remember, it's longer. So it's almost like its mouth is opened wider than normal, and so we can think of that as an obtuse triangle. It makes sense since this hypotenuse is opened wider. It's not a right triangle. In fact, it's an obtuse triangle because the hypotenuse is longer. And here's another example. How about 7, 10, and 8? I did this on purpose. I put the 10 there. But the 10, if that is a right triangle, this 10 has to be the hypotenuse. The hypotenuse is always the longer side. So I was trying to trick myself. And so I put the numbers in the Pythagorean theorem. And in this case, we get 49 plus 64. Does that equal 100? And the answer is no, it does not. It is not a right triangle. But in this case, we have this hypotenuse side is actually smaller. So I have this backwards here. This should be turned around this way, but it's, let me go over here. It's smaller. The hypotenuse side here is smaller. 113 is actually larger, so the hypotenuse side is smaller, and so this hypotenuse is smaller, and so that means that it is an acute triangle. And so the summary, if we have these if the sides of a triangle do work in the Pythagorean theorem, it is a right triangle. If the hypotenuse is bigger and the two sides, it doesn't satisfy the Pythagorean theorem, but we know that it's not a right triangle, and we can even say that it's an obtuse triangle. And here, if the hypotenuse side is smaller, it's an acute triangle. It's not a right triangle. Okay, so let's talk about the distance formula and the Pythagorean theorem. The last concept, and I add this at the last minute because it is an important point. And I wish I had space to put a triangle in here or a grid, but I don't. So I want you to just visualize these points being on the coordinate plane, being graphed. There'd be one point here at here. Oh, I didn't want to do that. There would be one point here at, let's say, 2, 3, and another point here at 5, 7. And so what is this diagonal length? Well, if we think of this, I'm just drawing this diagonal length. If we think of this, we could construct a right triangle, and we could find this length in the x direction and the length in the y direction. So if that's why I'm subtracting the x's, because that's the length in the x direction and that's the length in the y direction. So here's the Pythagorean theorem. Can we find this diagonal length, this hypotenuse, by finding the difference in the x and the y direction? And of course, well, if we do that, we have to take the square root to find this diagonal length, because it's not the square that we want. So this right here, we could change that h to a d, and it'd be the distance formula. And so I kind of explained it without a graph there, but so here's the distance formula. And so what is the distance between these 2 points? Well, let's use the distance formula. The x coordinates are 5 and 2, so in the x direction, it is a difference of 3. And the y coordinates are 7 and 3, and in the y direction, which goes up and down, we have a difference of 4. And so I used a very common triangle, and so we have 3 squared, which is 9, plus 4 squared, which is 25. And so we know that the length of the hypotenuse is the square root of 25, which is 5. And so the distance between 2, 3, and 5, 7 is 5, and we can subtract the x's and the y's and square it, add them together, and I've kind of shown you how we go from the Pythagorean theorem to the distance formula. And so there's an example. So thank you, and good luck with the Pythagorean theorem. Any questions? I'll see you at Zoom office hours and Zoom classrooms on Wednesday. Thank you, and have a great week, Mr. Forster.